Good morning. In today's session, we shall be discussing about the hydraulic design of sievers. In sanitary engineering, design of sewer plays a very important role, that is for the successive completion of a project or the successive working of a sewerage system mainly depends upon the design of sewer. So now there are two important differences that has to be considered when we design a sewer in comparison with the design of a water pipeline. So of course the general approach is same, out of which two major differences has to be considered. The first is that presence of particles. What does it mean by presence of particles? In a sense, the water carriage or the passage of water in a pipeline does not contain any of the particles. That means to say there won't be any external agencies which cause deposition as such. While when we are speaking about the sewage, it contains inorganic and organic particles, say for example that may be silt, grit or sand, which are more prone for settling in the inner surface. If and if at all, if those particles are not removed from the inner surface or not removed from the sewer, then those may cause clogging, which in turn may reduce the efficiency of the sewerage network. Say for example, if we have a sewer here, let us consider this is a sewer wherein the passage of sewage will be there, which contains grit, sand, etc. And then here I have the complete flow of sewage wherein the inorganic particles have the tendency to settle down at the bottom surface, thereby causing the deposition. But not all particles will settle down. The lighter particles will be floating or kept in suspension. So now I tell this is very important. Lighter particles are kept in suspension. What does it mean? What is that it is causing the suspension? So all that we are supposed to know is about the velocity which keeps those lighter particles in suspension, which otherwise may make them or prone them for the complete settlement, thereby causing the deposition, which in turn clogs the sewer. Upon clogging of the sewers, the efficiency is lessened. Efficiency of the sewer is lessened or reduced. So now, what happens if and if at all if the particles is not kept in suspension? Then those particles will keep on accumulating here on the inner surface, such that they won't be dragged outwards. They are not dragged outwards during the flow. So now it is the minimum velocity which keeps the particles during the flow such that they are not deposited on the inner surface, and that minimum velocity is known as self-cleansing velocity, which otherwise deteriorates the quality of the sieve material by making it more prone for abrasion and clogging. So what does it mean by abrasion? As we all know, the grit, sand, silt, etc., like these are all the inorganic particles that are erosive in nature, and that in turn while the passage of the sewage will make the sieve material abrasive such that the thickness of the pipe will be lessened. Next is that pressure. The passage of water is under pressure, henceforth it will have a tendency to move up and down in a hill, for example. So there may be a gravity flow, a pumping might be there, or the combination of that. In a sense, the dual system may be even there, while the sieve is considered as an open channel. That is because there the sewage is led to the downward direction by providing a proper gradient. So it is all important for the sieve to be laid at a proper gradient so as to suffice the continuous downward direction flow, which otherwise requires an external equipment for the passage. That means to say, then we are supposed to place a pumping instrument or an equipment so that the sewage will have to be pumped from one point to the another. So that becomes uneconomical. Moving on to the next thing, there are certain empirical formulae that are to be known prior to the design of. Once we know the factors that are influencing the passage of sewage, that is, first one is the characteristics of the sewage, second one is conditions of flow, inner surface, that is the roughness coefficient, bends or joints, shape and size of the particles, very importantly, area of the sieve. Keeping all this in mind, we shall know certain empirical formulae that are to be followed during the design of sieves. We have 6 empirical formulae for design of sieves. First one is Chedji's formula, which states that V is equal to C root of R into S, where C is the Chedji's coefficient, R is hydraulic mean depth, which is denoted as such. Now, S is equal to slope, V is equal to velocity of flow in meter per second. We shall see that hydraulic mean depth is in meters and that is obtained by R is equal to A by P, where A is area of the section. If the sewer is running full, area of the section is pi d square by 4 and perimeter is pi d. Upon simplification we get d by 4. So, we are supposed to consider R is equal to d by 4 if and if at all if we are designing the sewer for running full. Next, we shall know certain factors that influence adopting Chedji's formula for the design of sewers. Chedji's formula depends upon the shape and size of the particles, very importantly the specific gravity of the particles, roughness coefficient, roughness of the sewer material and velocity of flow. Next is the basins formula. Which states that C is equal to 157.6 by 1.81 plus m by root r. We can just observe here the value of C that has to be incorporated in Chedji's formula can be adopted from this formula, that is using Basins formula, or one more we have Cutter's formula. So, we can calculate the value of C using this formula where C is equal to the Chedji's constant. Next one, Manning's formula, which states V is equal to 1 by n r to the power of 2 by 3 into s to the power of half, where n is equal to Manning's constant that varies from one pipe material to other pipe material. Moving on to the next, that is Cutter's formula, which states that C is equal to 23 plus 0.00155 by S plus 1 by n, the Manning's constant, again 1 plus 23 plus by slope S n by root r. So, we can just observe whatever the value of C that has to be obtained in case of Chedji's formula, in case of using Chedji's formula, that C can be calculated using either Basins formula or Cutter's formula. Next is Crimp and Bridges formula. Which is used to calculate the velocity, which states that V is equal to 83.47 r to the power of 2 by 3 into s to the power of r, where again V is velocity of flow in meter per second, r is hydraulic mean depth in meters. Fine. Next is the very important Hazen-Williams formula. This formula is very much applicable for designing the sieve which carries the sewage under pressure. So, this states that V is equal to 0.849 CH R to the power of 0.63 and S to the power of 0.54. So, CH is the roughness coefficient. Moving on to the next concept, it is maximum and minimum flow velocity in sewers. So, a designer has to keep in mind about the velocity such that the velocity should not be too minimum nor it should exceed the limits. It means to say that whenever the particles from the sewage will settle down in the sewer material, that is inside the sewer material, rather than being in suspension or flowing away, it causes the deposition. So, this deposition has to be avoided. To avoid this deposition of particles, we require a velocity. We require a minimum velocity or what we call as a self-cleansing velocity, so as to make those particles move away or flush away from that surface. That is what we mean by self-cleansing velocity. The self-cleansing velocity is not constant, means to say throughout the day we cannot achieve the same self-cleansing velocity, means to say the velocity will vary depending upon what is the water that is being supplied to us. So, that velocity will depend upon the water that is supplied to us. So, that in turn will be converted to sewage, right. So, we will not be supplied water in the same mode throughout. There shall be the fluctuations or variations in the supply of water. Henceforth, we cannot achieve the self-cleansing velocity a constant throughout. It varies, and very importantly, at least we should achieve self-cleansing velocity once in a day, so as to make sure that there won't be deposition of any of the particles inside the surface which will clog the sewer so as to make it non-working or so as to reduce the efficiency. Next is the maximum velocity. As and now we know that we does not want a velocity which is lesser, means to say which cannot flush the particles. Likewise, we don't even want the velocity which is more than the limit, means to say the particles while passing away from the sewer should not cause abrasion or should not cause wear and tear to the inner surface, or in a sense the smoothness of the surface should not be hampered. That means to say that there should not be a scouring velocity. So, which means the velocity should not go beyond the limit. Scouring means the removal of a portion of the sewer material here should not happen, such that there won't be any deterioration in the working space of the sewer. So, now all I want to tell here is the velocity should neither be too small nor be too long, or it should not be too high so as to cause the scouring of the inner surface. So, that velocity which do not cause deposition of the particles in the surface is known as the maximum velocity or non-scouring velocity. So, now I will tell very precisely whatever the velocity that is less than the self-cleansing or less than the minimum velocity is also not appreciable, along with the extended velocity or the maximum velocity. So, the velocity should be in between these two so as to suffice the good design of the sieve. Why is the velocity a concern here? Because if the velocity is not selected suitably, then it hampers the gradient, which in turn causes the deterioration or the lessening of the efficiency, thereby causing hindrance for the passage of the sewage. Or otherwise, in one more sense, what we can tell is, if the gradient is not proper, that is, if the slope is not properly selected, it causes the unwanted velocity, which means to say that the excavation required will be very high. Means to say, if the slope is selected in such a way which requires extensive excavation, then it would be uneconomical. Why uneconomical? Because in those instances, the infrequent intervals or in between the intermediate points, we are supposed to place the equipments like pumps so as to suffice the passage of sewage. Of course, that is uneconomical. Hence, in those instances, we are supposed to select appropriate gradient. But one thing I can tell, not always we will have a suitable gradient. Of course, we will have to work in conditions wherein there will be a mere flat surface also. In those instances, we will have to go for steeper slopes. In turn, we will have to go with deeper excavations, so as to make provision for proper achievement of velocity. So, what does it mean by proper achievement of velocity again? The velocity that I am achieving over there because of the gradient selected should be such that it should not be a non-scouring velocity, or it should not be a velocity which is minimal so as to keep the particles in suspension, or the velocity should not be a scouring velocity, thereby causing the removal of the surface inside the sieve, which cause abrasion, which cause the reduction in the thickness of the working area within the sieve. Now, we shall design a sieve using the following data. A main combined sieve is to be designed to serve an area of 20 square kilometer with a population density of 250 persons per hectare. Full stop. The average rate of sewage flow is 350 LPCD. The maximum flow is 15% in excess of average, together with a rainfall equivalent of 15 millimeter in 24 hours, all of which appear as runoff. Determine the capacity of the sieve taking V is equal to 3 meter per second. So, now let us take down all that, shall write down the data that is given in the question. So, first of all, it is a combined sieve. So, first of all, we shall write down the data. First, area is given, it is 20 square kilometer. Population to be served is equal to 250 persons per hectare rate of water supply is equal to 350 LPCD. Rainfall intensity is equal to 15 millimeter per hour. Velocity is 3 meter per second. So keeping all these in mind, we shall design a circular sewer. So first of all, the area given is 20 square millimeter. With that, the population of 250 persons has to be supplied a water of 350 LPCD. Total population of the area is equal to 250 persons into 350 LPCD. So the solution is, as it is been given in the data that 20 square kilometer of the area is to be served with a combined sewer, is to be served with a circular sewer, which suffice the population of 250 persons per hectare who has the rate of water supply of 350 LPCD. So now, first of all, it is the total population of the area. So here we know it is 250 persons in a 20 square kilometer. Since it is square kilometer, so we will get 5 lakh persons. So now next one is that we are supposed to calculate the average sewage flow, because we have the rate of water supply. So in turn we are supposed to calculate what is the average sewage flow from this rate. It is 5 lakh population into 350 liters per day, which means to say it will be around 175 into 10 power 6 liters per day, or 175 million liters per day. So we shall convert that into meter cube per second. 175 into 10 power 6 divided by 24 into 60 minutes into 60 seconds, we get around 2.025 meter cube per second. So average sewage flow at the rate of 350 LPCD is 2.025 meter cube per second. But we will have to remember that whenever we design a sewer, we design it for the peak flow. Why we are supposed to design it for peak flow? To achieve the desired velocity, that is to achieve the self-cleansing velocity or the minimum velocity, and this non-scouring velocity, that is the exceeding velocity or the maximum velocity. We will be designing for peak flow. So now here maximum sewage flow. So the maximum sewage flow will be 1.5 times the average flow. It is been given in the data that the maximum flow or the peak flow is to be considered as 1.5 times. So it is 1.5 times the average flow. This will come around 3.038 meter cube per second. So now it is a circular sieve. That means to say in the data it is been specified as storm water, that is intensity of rainfall is given as 15 millimeter per hour. So we will have to find out the storm water flow even. So since the area to be served is 20 square kilometer, rainfall is 15 millimeter per hour, therefore it is 1 by 24 into 60 into 60. So now we get around 3.472 meter cube per second. So now I have the average sewage flow from which I calculated the maximum sewage flow, which means to say I have the quantity of domestic plus industrial here. So this is one portion of the sewage. Now I have the storm water even. Together with these two, I will calculate the combined flow. Therefore now, very important, total flow in the combined sewer. So the combined sewer means I have to add the flow from the sewage along with the storm water. So here I have 3.038 plus 3.472, I will get 6.51 meter cube per second. So the capacity of the combined sewer should be such that it should be in a position to accomplish 6.51 meter cube per second flow. So now the discharge here is given by Q is equal to A into V. I know the value of Q, it is 6.51 in meter cube per second. I know the value of area. Since it is a circular sewer running full, I am considering area as pi d square by 4 into velocity is 3 meter per second. So now upon simplification, I get the value of D as 1.7 meter. Hence, provide a circular sewer of dia 1.7 meter.